In this video, I'm going to show you how I made a Hero type of steam engine and Aeolipile using just a standard toilet tank float, and I then demonstrate how it works and take a thermal video of it spinning with steam. I think you will find it informative and interesting. Hero of Alexandria, also known as Heron of Alexandria, around 10 AD to 70 AD, was a Greek mathematician and an engineer who was active in his native city of Alexandria, Roman Egypt. He's often considered the greatest experimenter of antiquity, and his work is representative of the Hellenistic scientific tradition. Hero published a well-recognized description of a steam-powered device called an Aeolipile. They sometimes call it a Hero engine. By the way, this information is from a great article in Wikipedia that is well worth reading. This is a link to it. This is a graphic representation of Hero's steam engine. Basically what you've got is a cauldron, probably made out of copper or bronze. I'm assuming it was copper for this. A couple of hollow tubes here going up to a hollow copper sphere with some small copper tubes and small orifices pointing in different directions like this. Okay, now this cauldron would be partially full of boiling water generating a lot of steam. Large amount of steam would help compensate the leaks that you might get at this junction here. This is a possible problem. They wouldn't have had good high quality rotary unions back then, so I'm not quite sure how they did that, but enough steam you could afford a little bit of leaking. But basically what happens is steam exits small copper orifices here and here, causing it to rotate. And since steam, well, really what we're talking about is water vapor, is relatively low density. And so you have to have pretty good velocity for it to be able to spin this thing and minimal rotating resistance. I've always wanted to make one of these things, and when you start working on it, you realize the distance of the nozzles from the center of the rotating axis affects the torque on it and how easily it can rotate. Also, if they're too long, they can cool off, and you don't want that. You want to maintain heat to keep it the steam blowing out of the nozzles rather than just condensing. So anyway, I came up with an idea how I could do this about a fancy metalworking shop, and this is what I've been able to do. This is just a standard copper toilet tank float. I had to purchase it off Amazon because they're not as readily available these days. Just trying to mimic what Hero of Alexandria used in his Aeolipile. Now in his design, it was spinning horizontally. There were some complications trying to do that. Things you got to keep in mind with this is to get any kind of thrust to make this thing spin, you got to have high velocity since it's just water vapor. If it was squirting water out, it wouldn't take so much, but very, very low thrust with this with steam. So at the relatively low pressure we got here, you got to have very, very low rotating resistance. And the way I've done that is I've actually, what I've got on top here is I soldered in a 1/4-inch brass fitting. Just use a punch through that copper. Household solder, lead-free with some flux. This is an adjustable brass and stainless pressure valve, pop-off valve that I got from Amazon, adjustable from 0 to 100. I've got it arbitrarily set at 30. This is just a finishing nail that I ground off the end and smoothed up a little bit to fit down in this, actually just a Phillips head screw there. And on the bottom is a female thread on this device. I think it's 1/4-inch, 20 threads. So it'll screw onto a standard toilet tank lever arm. 1/4-inch copper tubing to get the right opening here. I found that you can't just use tubing, you won't get enough velocity. You got to have very, very small opening. Little hard to see, but the way I did that was I put in just a paper clip into the end of the tubing, mashed it with some pliers, and got that controlled size opening on both sides. And put 50 milliliters of distilled water in this through this port here, and put a little oil on the bottom. This is also a pointed nail down here. So we'll put some heat to it with this MAP gas torch I have and see what happens. I had a MAP gas torch rather than propane. Either one would probably work. It's important to keep it directed towards the bottom third of the copper float there where the water is. Otherwise, you could melt the solder if it gets up too high. The boiling water will keep the temperature down to 100 degrees Celsius. I always wear safety glasses for all my experiments, but it's very important that you wear at least safety glasses. A face shield is also highly recommended for this type of thing. Even though this is relatively low pressure, you never know something like this, and keeping the water volume down will also minimize any hazard. As you can see, this device worked really well, better than I expected actually. And actually, just for fun, I decided to use my FLIR 1 Pro thermal infrared attachment from my iPhone to take infrared video of this. So we'll do that and see what that looks like. It's important to note that this infrared video is good for showing relative temperature differences. The brighter colors, white, yellow, are hotter. Darker is cooler, like blue. And you'll notice the bottom half of this and around the torch is very hot. The top half, as you would expect, is a little bit cooler. So don't worry about the temperature numbers there in the center. At this point, I don't think they're relevant, but this does a good job of just showing the relative differences in temperature across this device. So I hope you enjoyed this. If you did, please like the video, click on the round Anisotropic Plus subscribe button that'll show up here, and check out our other links. We'd appreciate it. Thank you.